just briefly introduce Rick Report from the University of Huntsville, Alabama, has a very interesting concept of beam optical power.
That's it? Okay. I'm going to talk from over here. Do I have any more cord here?
Yeah, let me work on that.
I'm just trying to get something illustrated with a light there. Thank you. I'm used to teaching classes on material. I'm used to being interrupted. I love questions. So at any point in the talk, please feel free to step in and ask a question. I will try to respond. But the concept that I'm going to talk about was developed by myself and the students in my group, interacting with other people working with NASA. I've had some funding from DOE as well as from NASA. The next view graph. The thing that I'm going to talk about is an optical power infrastructure in Earth-Moon space. The shortened title said in Earth. I want to be sure that it's understood that we're talking about Earth-Moon space. The concept is to support the vision that has been announced by President Bush, basically making a venture into space starting primarily with the Earth-Moon region here initially, and then gradually extending further out to Mars and to other locations. The focus at this time is in this range, this area that's nearer to the moon and the lunar surface. The methodology is basically the point here is that there's billions of terawatts of power available as sunlight in Earth-Moon space, far more than you'd need for the needs of Earth in the projected future, far more than you need for space exploration. The challenge is to make that sunlight useful. Sunlight is hard to move around and shift and deliver. What you need for an optical power infrastructure is what NASA calls an energy-rich, flexible system where you can have virtually anywhere, virtually any time, the amount of power that you need in a needed form. So the goal is to create, using coherent light, a power infrastructure in Earth-Moon space that is analogous to our terrestrial electrical power infrastructure, which is based instead on coherent light. And the point I'm going to, the line of reasoning that I'm going to pursue here is that we can make the argument that there's plenty of energy out there. The problem is you can't really move it around very easily as sunlight. On the other hand, there are ways, I will argue here, and discuss that the principal need is to develop four basic technologies. You have to mature some simple technologies that will allow you to take advantage of that power and to deliver it where you want it when you need it. The idea is this, that in order to be specific, I'll give this in terms of a particular example of a particular infrastructure. You can envision alternative approaches, but the concept I'll talk about is basically one of having energy farms located on the lunar surface. A likely location would be the north pole of the moon, where you have what they call almost eternal sunlight. You always have sunlight accessible. The power could be beamed from there to relay satellites at the L4 and L5 points, to satellites in geostationary orbit around Earth, and then from there to satellites that would be in low Earth orbit. And the point here is that if you start from the right place on the moon, you can basically, anytime you want, you can send power anywhere you want. You can send it to the dark side of the Earth, you can send it to the non-illuminated side of the moon. You can basically deliver the power anywhere. Next graph. The concept here is to reach regions by going by the relay mirror. I'm going to basically head for my normal finishing time. All right. The need for the relay mirror is that if you don't have a relay mirror, there will be times when you can't reach, for example, the side of the Earth that is facing away from the moon. The size of the relay mirrors that you need is about a 50-meter aperture. That's big. But that size aperture is being explored at this time. Matter of fact, up to 150-meter mirror sizes for space by a DARPA program called Project Classic. So this technology is consistent with technology that's being explored at this time. This is the bottom picture is what the beam would look like if you could see it in space. Actually, there's very little in space, so the scattered light would be very weak. In principle, you could take an image with a long exposure camera. The beam would go from the moon to a spacecraft, which would be, for example, in geostationary orbit. And if you were out here looking in, this is the way it would appear to you. You'd see the beam delivering power to a spacecraft. The point, of course, is that now you're delivering the power to the spacecraft, so you don't have to carry fuel, which is an enormous saving. Also, if you had supply depots, as the previous speaker was discussing, you could supply energy to the depot. You could take water and turn it back into oxygen and hydrogen, for example. Next graph. You could also use such a system for surveillance, for example. One of the big problems we have was the area of Earth that needs to be monitored for activities that you might want to discern very quickly is difficult to cover because there's so much space. You could put an array of satellites in low Earth orbit that can monitor a large area. It's important to make those satellites inexpensive and small. We prefer not to have to provide them with their own power source. With a system like this, the power could be beamed from the satellite in geostationary orbit to any one of an array of satellites in low Earth orbit. Say you have a suspicion that some particular biochemical weapon was released in a particular area of Earth. You could direct power to the satellites in that area. They could monitor it and give you a map of what was released in that area and where it's distributed and how it's moving in time. Next few graphs. You could also deliver power to Earth. The strategy you could have a location where you wanted to deliver power as a green beam to make it safe. We look very carefully at the questions of safety. You can deliver the power quite well within federal safety guidelines. If you want to protect the beam itself and make it more concentrated, you can put a safety beam around the power beam. And basically, if a bird starts to fly into the beam, you can discern the presence of the bird and turn the beam off, for example. So there are ways to take this power and deliver it to Earth as well, in a safe way, as well as to other locations. Next few graphs. This gives you an idea of the size of aperture that you need to build for delivering power to these distances. The relationship looks like this. This is the length that you want to go, the distance you want to go. This is the size aperture. For the distance to the moon, 384 megameters, you need an aperture of about 30 meters. Power, a little bit more or less depending on the quality of the beam. Next few graphs. Okay, again, one thing that most people don't think about is there's an enormous amount of power out there, billions of terawatts. The power that's used on Earth is sort of terawatts. There are billions of terawatts available. Sunlight, you can't access sunlight because the angular divergence from the sun, which is an extended source, makes it such that to try to relay it with linear optics, conventional mirrors, you just can't deliver the power where you want to. But with coherent light, you can. In particular, the choice is to use lowest order Gaussian modes. And at the receiving site, another concern is to then take that power that's received as coherent light and transform it into a form of power that could be used for typical purposes in space, such as electrical power next to graph. Okay, the barriers to accomplishing this kind of power infrastructure, which we do with light in space, what we do with electricity on Earth, are basically technical. They're not fundamental physical laws. Fundamental physics allows you to do this. So the question is, what do you have to accomplish in order to achieve this? And I've taken 4 technologies that you'd like to develop. This is one of the steps you need to do is concentrate the sunlight that's available in space. You cannot create coherent light without achieving a certain basic intensity in a certain volume. So the first task is to concentrate the sunlight to the level where you can actually transform it into laser oscillator power. None of these 4 steps have been accomplished to date, but my argument is all 4 of them are feasible, and feasible within the 10 to 40 year time frame. The next step, having concentrated the power, achieving laser oscillator action, you have to remove heat. It's an unavoidable product of the process of making sunlight energy into coherent energy, that you have to create some waste heat. Having created that heat, you have to move it out of the volume where you've created it. The obvious material is solid-state laser material. Gases tend to be difficult to handle. You have to pump them and move them around. You can't move the heat out quickly. Semiconductors are too small to handle the power level. About the only real serious candidate is a solid-state material. After you've gotten the power into this volume and taken the heat out, then you have to transfer the power that you put in this solid-state material to a coherent optical mode, which again I'll argue is possible, but you have to do some very specific things. And finally, having created the coherent light and being able to transmit it over these long distances, you have to convert it efficiently to electrical power at the receiving site. Next graph. How do you do this? This is a design that we've developed using ASAP, an Advanced Systems Analysis Program, the software. It costs you about $40,000 to rent it for a year. Because we're a university, they allow us to use it free of charge. It's very powerful. It was developed originally to handle scattered light on the Hubble Space Telescope. We've used that to develop a design for a concentrator that concentrates sunlight through. It has collecting mirrors out here. They come in, they go through non-imaging concentrators, they go into a set of tapered ducts. There's a doped core. This is titanium sapphire is what we're using as the example. And then the core of the power is absorbed into the laser gain material and is now available to use at the needed intensity, which is about, you get an integrated power for the light that sweeps through this core. It's available, it's the order of 50 kilowatts per centimeter squared. Next view graph. The way in which the light ends up in this core and is concentrated, you have a combination of these multiple collecting cones, and the rays are brought into, they bounce a lot inside this tapered duct, but because the core rod here is absorbing, the power is absorbed in the core. For those of you who are familiar with fiber lasers, this is like the double-clad fiber laser strategy, but it's a way to concentrate power, basically. Next. This is, again, the point of view is you're basically, what you're doing, you can think of it this way if you like, because the laser field will sweep out this rod-like volume in the core and collect the power in there, you can do better than, there's a classic fundamental thermodynamic limit on the intensity that you can achieve in a planar region. It's set by thermodynamic laws. However, the goal here is not to concentrate that power in a planar region, but in this rod-shaped volume. Once you get it into the rod-shaped volume, this is what you want to convert it to laser light. The laser light, the beam that propagates through this region, basically adds up all the light that's there. So, in effect, you collect power as though you were collecting power from multiple suns. This is as though there were 16 suns that you could collect power from. This is enough to get over the threshold you need to access to get the required concentration of power. This is an end view. You're bringing the power and you're putting it in this one location that's swept out by the laser field. You get basically an intensity of the laser field coming out of the system that is substantially higher than the intensity of light at the surface of the sun. So this is something that's kind of counterintuitive. A lot of people don't really appreciate this, but you can take sunlight, and through this strategy, you can basically achieve an effective concentration of light that's far in excess of the intensity of light at the surface of the sun. Now you've got a form of power that you can use to do a wide variety of tasks, including propulsion, that could not be done with conventional light mixed. This shows an image. If you had 4 of these cones, this is what the collecting optics would look like. They have a scale of roughly 25 meters by 40 meters for the collecting optics. You can make some estimate of what this mass to volume ratio is. for the collectors in the system, about 4 kilograms per kilowatt. Next view graph. Okay, how do you remove the heat? You paid the price in that you've concentrated the power to achieve the laser oscillator action, but now you have a lot of heat in a small volume. You have to remove that heat or things are not going to work. That's been the showstopper for scaling lasers to high power. The catch here is that when you try to remove the heat in this quantity from a small structure, the rod-shaped device that we've got the power in for 100 kilowatts is about 3 centimeters diameter and maybe a meter long, something like that, maybe 2 meters long. By taking the gain medium, instead of making it a rod, which would basically not work because of the gradients in the temperature causing thermal lensing, you basically put in barriers into the structure so that the heat in the medium is localized in a gain disk here, which is adjacent to a cooling disk of undoped sapphire, so that the heat that's in this region here leaves axially. It creates no radial thermal gradient, so you don't get thermal lensing, and then it propagates outward in the undoped sapphire. For temperatures in the 100 degrees Kelvin range, we can achieve a distribution of temperature in the high sapphire that is hotter here, cooler here. The adjacent piece of undoped sapphire is cooler here, hotter here. This is just the opposite of this temperature profile, so that the net consequence is that there is no net thermal lensing. This overcomes one of the principal barriers to scaling solid-state lasers to the high ridge power and high beam quality that's required for such a system as this.
What's the length scale on that?
What I'm showing you is each of these individual discs here is about a millimeter wide. So I'm just showing you a small piece of the gain medium.
And the diameter of the whole business?
And the diameter here is about 3 centimeters.
Okay.
I'm showing you illustrations for a design that will give you about 100 kilowatts of power. It turns out that the current goal for solid-state laser, high-power lasers that could operate in the not too far distant future is about 100 kilowatts. And so I've taken that goal because this is sort of the current goal. Again, we're talking about the problem of removing the heat from this region without having the thermal distortion. There's also a thermal stress induced by refringence and a thermal shock fracture of the crystal if it gets too severe a gradient. By using this strategy and overcoming the thermal lensing and the thermal stress induced by refringence, we can lengthen the gain material far enough so that the heat is dissipated over a long enough region that we don't run into the thermal shock problem, which basically shatters the crystal next to your graph. Another problem that you run into if you're trying to do the technology here is that you have to, if you've achieved this concentration of power and you've handled the heat, you still have to now take that power that's available in the solid-state laser rod and remove it so that it shows up in a lowest order Gaussian beam. How many people know what a lowest order Gaussian beam looks like? How many have seen a laser pointer? Okay. The laser pointer works because it's essentially a lowest order Gaussian beam. You point it, and you get this slender beam that goes quite a long distance without spreading very much. The whole secret to this optical power infrastructure is that you go to a lot of work to get the energy into a beam that has that character. You send it a long distance, like from the Earth to the Moon, and it spreads by a small enough amount that you can actually deliver the power to the place where you like to send it, even though it's a long distance. You could not do that with any other kind of light. The way you get the power into that mode is you have to build a particular optical resonator that looks like this. This is the beam path. This is about 3 meters for the 100 kilowatts. Next view graph. What you're going to do is you're going to put your gain rods in this region of this resonator. Next view graph. And if you put some constraints on the size of the beam here, choose this geometry, pump it in the way that which I described, this structure, and this is about the only structure that would do what you want, will transform the energy in the solid-state laser rods into this lowest order coherent beam. for a large diameter beam that you need to handle power. This is basically the purpose of this was to take is to take a situation where you want to create something like the laser pointer beam, but you want it to have enough power in it so it's going to deliver serious power to some place like the National Space Station or a supply depot or another location on the moon or a location on Earth. This is all to get up to that power. You have to get a fairly large area beam. And it turns out the geometry and the size of the structure is difficult to manage. If we did a conventional laser resonator, it would be kilometers long. Next few graph. Okay, so technically, advances that I described, 1, 2, and 3, will get you a way of collecting the power, transforming it to the lowest order Gaussian beam so you can transmit it, and you can now get it where you want. Next few graph. You still have the problem that when you get it to the receiving site, you really like to put it in a form that you want. The coherent light is very useful in many ways, but typically you're going to want something like electrical power if you're on the space station, for example. Because the laser light is monochromatic, has a narrow frequency range, you can adjust the frequency of the light so it matches exactly, very closely, the photovoltaic band gap. When you do that, if you optimize everything else, you can show that the principal remaining limitation is the fact that there's a finite temperature of the material that you're illuminating. This gives a plot of the efficiency for an idealized photovoltaic, which is not easy to do, but which is something we're working on. We've done a laboratory case on an old photovoltaic. We got 60% efficiency. This is what you could anticipate achieving if you worked on the technology and refined it, say, over the next 40 years. The efficiency gets up into the 90 percentiles. This is for the incident wavelength you'd be using. 1 micron is typical. These are the temperatures. This is room temperature. This is the lower temperature, and shorter wavelengths tend to give you an advantage in transforming the power. But the point here is you've got a way to collect the power from the sun. That's your energy source. You're paying nothing for your energy source. And for all practical purposes, it never runs out over our time of interest. And when you can take that energy, you can put it into form, you can transmit it anywhere in Earth-Moon space. And then having transmitted it, you've got a strategy for transforming the received power very efficiently into some alternative form of power, like electrical power for an ion engine, for example. Next few graph. Okay, that's the concept. Now the thing we're working on at the University of Alabama in Huntsville, I have a group that does research work. One of our contracts is to work on developing this technology. I'll talk a little bit about our actual experimental work here, where we're actually working on developing the device that will take power like sunlight and transform it into coherent light. So in order to demonstrate this cell that I talked about at the beginning of the talk, where you have a gain medium that's excited by light, principally the green component of sunlight, and that power is then transferred to an adjacent piece of material, which is going to be the cooling material. We take a sample of 2 pieces of sapphire, put them in a interferometer that's a Michelson interferometer. We'll send in a probe light, then we'll look at the interference pattern here formed in the interferometer of the sample. Now what we're going to do is we're going to watch the power that we put in here basically spread through the volume here, so we can actually see the temperature of the material as a function of time as the heat is moved out of the gain material into the cooling material. Next few graph. This is a picture of what some of the sapphire crystals look like. There's a piece of titanium doped sapphire which will be heated. There's an adjacent piece, similar piece of undoped sapphire. We're going to watch the power go into the titanium doped sapphire and then to the undoped piece. You have a question?
Yeah, now, this cooling process is to keep from destroying
the crystal.
The excessive heat.
Yeah.
Would destroy it if you didn't.
Yeah, we have to get the heat out. If we left too much heat in too long, it would break the crystal.
And about what percent of your energy you lost did you have to sacrifice for this?
You typically, in a real laser like this we're talking about, you have to give up about half of the pump energy. It's about 50% efficient. If we, if we get real clever and do tricks, there may be a way to boost that to 60 or 70%. But, of all these example is worked out on sort of a half of the light gets used concept. Next graph. What I'm going to show you is a movie that shows what we've done is this is an image of the light transmitted through the two blocks of sapphire. This is the doped one, this is the undoped one. What you see are the fringe patterns in the two blocks that are separate. You see the boundary between the two. And by looking at the fringe pattern, we can then, as you put the power in, the blocks heat up. The heating up of the block changes the optical path length of the material. We can read off the temperature from that change, and we can give you a map of the temperature change in the material, and then we can follow that development in time so we can actually see the heat flow in these blocks of material. And this is a three-dimensional plot of this is higher temperature. Where it's red, it's hotter. Where it's blue, it's colder. Over here, this is the adjacent block. This is the initial frame of the movie for the heated block. Next view graph. Okay, these are what we've got. If they will run here, will be two movies. One is in 3D. One is basically a section taken through this set of data here that will show you how the heat moves. The interface, it lies along here. So what you're going to see in this display here is the heat has been deposited here. We're looking at the block at the moment after a laser pulse has put the heat in. Boom. So this is immediately the temperature goes up where you put most of the energy. And if you'll double click on this, hopefully this will run. What you're seeing is the heat spreading out now in the block of sapphire, and it's basically moving across here into the undoped sapphire. So the point of this is this small block is not going to go up into space itself, but the big challenge in this scaling of lasers to handle this type of power has been getting a handle on the way in which the heat flows in these materials. So this technique is basically an experimental tool for us to monitor to what degree we've succeeded in this management of the heat. Now, if you double click on this one, this is looking at a section. You'll see the heat flow out from this heated region, and it begins to move over into the adjacent block, and eventually the whole system cools down. So you're actually getting a chance to go in and see what happens. This is one of the tools that we'll use in trying out different versions of the concept that we proposed. Next view graph. Okay, what can you use this for? One of the areas that has been looked at of interest is how to protect Earth from Earth crossing orbit asteroids. MN 2004 is one of the asteroids that was slated to, is projected to visit the Earth around April 13th of 2029. So one of the applications that you could use one of these lasers in space for would be to deflect the asteroid from hitting Earth. And I'm going to give you some numbers here, an example here. The thing that is a surprise to most people, you can give me some feedback whether this is a surprise to you or not, is that it really doesn't take a lot of laser power to move a big asteroid. Part of what works is if you give yourself plenty of time, which is an important lesson in life, if you give yourself plenty of time, that you can take a very modest push and you can do a lot with it. So I've taken the example of MN4, 2004. It weighs 46 million metric tons. We have about 25 years before it shows up here. You can calculate if you apply the laser beam to the asteroid, you create a push on it. As it moves, it tends to be deflected from its unperturbed path. It takes a quadratic path that has this form. The time comes in squared because the sooner you push, the more time it has to deflect. The amount of power that you need is relatively small. Now, the reason it doesn't take a lot of power, this is different from a solar sail. You're not trying to use the momentum of the photon to push the asteroid, what you do is you configure the laser so that it produces short pulses of light. The light appears as short pulses. The light from the laser strikes the surface of the asteroid. You're optimizing the system, but you want to use that power effectively, so you basically design the laser to make these short pulses. The short pulses strike the surface of the asteroid at high intensity. The intensity is so high that it instantaneously heats up. This is like the crystal fracture, but you're deliberately going, on purpose you're causing the fracture. You basically explode the material off of the surface of the asteroid. The material, as it leaves the asteroid, leaves it at a high velocity, about 10 to the 4th meters per second. The reaction from the material being ablated from the asteroid creates a reaction force on the asteroid that pushes it. You get a lot more push from the light by using this method as opposed to just photon pressure that you might use on a sail. So you actually get a lot of thrust. It turns out, you do the numbers, for this particular 46 million metric ton asteroid, which we're concerned about, it only takes about 6 kilowatts of average power applied over that 25-year period, and I've assumed that I use it at maximum efficiency, so you probably need somewhat more power. But this power from a laser is not very different from the power that's used in a typical welding laser these days. So, you see articles where people, you're going to need, 50 megawatts of laser with a nuclear reactor to run it, to push the asteroid. Not true. You could go down to Walmart, almost, not quite, but almost, and buy a laser off the shelf, and if you could get the laser up there and you could run it the right way and you could use it efficiently, you could push MN4 away from Earth. You can say this. Next view graph. To illustrate the pushing, we made a little movie here. Hope this works. What this is going to show is how, as you push on the asteroid, in time it takes a path that has this, it's deflected, and it has a quadratic function in time. This is, the horizontal axis is time, which in this case is also distance. This is terameters. That's a 25-year trajectory. This is the distance which it moves in terms of, this is megameters. This is about 40 megameters here. This is the Earth, the dimension of the Earth is about that size. So you're moving it by a number of Earth radii over this 25-year period. Next view graph. Double click on this. Okay, this is a case where you got the laser, but you bought the budget version, and it didn't have quite enough power. And the problem when you do that is that everything is fine. You're all set to miss Earth, but you forgot about the gravitational pull of Earth. So as it begins to approach Earth, the gravitational pull of Earth takes over, and it pulls in, and you have the collision. So you buy a better laser. Next view graph. Double click on this. This is a case where you bought the Model 2, and you did better. You actually got a near miss. Of course, you're going to cause some tidal waves and things like this, so that's not too good. Let's do the next one. Okay, now you really went out and got the large economy sized, and now you miss Earth by quite a bit, and the gravitational pull deflects it a little bit, but you clearly miss, so we can all rest easy. So the moral is don't get the budget version. Be sure you get the economy size. Yes.
Where are you putting the laser in this? I mean, you see that if the laser is near Earth and you're shooting at something that's 25 years away, you're pretty much just able to hit the front of it.
No, this is a good question. If you sit on the moon, you have to do some work with relay mirrors to deliver the power in the optimum way. What we're talking about here are asteroids, which are objects that typically, if you look at the trajectory for MN 2004, which is the example here, it basically co-orbits with Earth. We're traveling around the sun like this together, pretty much. So it's doing the same trajectory for 25 years. It's just that eventually there's a place. If you look at those trajectories carefully, eventually there's a point where the two come together, and the relative velocity is enough, 5 kilometers per second, to cause a lot of trouble. So the easy way to do this, if you're good at space stuff, is you build yourself a spacecraft, and you fly it out, and you sit next to the asteroid. You sit between the sun and the asteroid. You go off a couple kilometers from the asteroid. You collect the power from the sun to drive your laser, and then you just ride along with the asteroid, and you've computed, hopefully correctly, what the trajectory is going to be, and you you know what you have to do to change it in a way that's going to miss, then you just sit there and you push on it. And you can push because of this ablation effect. The spacecraft, you don't get you're not really pushing like with a stick. Because if you did that, your spacecraft would go the other way. But because you send the light, which has no momentum to speak of, from your spacecraft, it reaches the asteroid. When it reaches the asteroid, it blows the material off the asteroid. The reaction of that stuff coming out the asteroid pushes the asteroid. So you can just ride along with it. You can push it away, even though you're millions of times lighter than the asteroid.
Okay, suppose that you wanted to find an asteroid that wasn't going to intersect Earth and bring it up close to use as a mine or other material utilization.
You probably get into a lot of trouble with a lot of people. The point is you can, they're getting so they can predict these trajectories pretty well. One of the problems is, though, that you can't predict them perfectly. And you have the problem, 2004, this asteroid is probably going to miss us in 2029, not to worry. The catch is that when it misses us, the gravitational pull that causes that bending that you see will probably be enough to change the next set of trajectories. And it's going to come back in another 5 years after that. And at that point, you really are no longer sure what it's going to do. So the take-home lesson here is you really need to be able to predict these trajectories very accurately. And we'd like to be ready with the spacecraft and this system to use soon enough, so you can go in and start pushing, several years in advance at least, because that time helps you out a lot.
Yeah, well, okay, suppose that we...
Everybody keep it, when this guy goes out of the room, everybody keep an eye on him, okay? I'd like to report on what he does.
Suppose we twiddle our thumbs for 20 years.
Bad idea.
And we say, okay, we got 5 years now. Now how many watts would it take?
Well, there's been a careful study of this by some of the people at Langley, I think it is. And what happens, of course, it's a linear trade-off. If it takes you 6 kilowatts for 25 years, you wait to 1 year, then you need 25 times as much. No, wait a minute, it goes as square. It goes as square, t squared. So you need 25 squared. You need 625 times as much. So the people who project this correctly want to build 50 megawatt sources. Because they say, well, what if we've not prepared and we're caught and we've got to do something real quickly? My argument to you is the thing to do is to build some of these relatively low power systems and use them, because at a kilowatt, the beam size, if you're going to send it anywhere in Earth Moon space, is so big, it's at 30 meters. The power that you're sending over these distances is not very different from the power of conventional sunlight, regular sunlight. It's pretty safe. But if you let these guys get you into the argument that they've got to build a 50 megawatt source, now you've got a serious weapons class laser up in space. So you could be suspicious that maybe the reason they're talking this up is that they have an idea of maybe using that for something else. So my point is, you don't need a weapons class laser to push an asteroid. But you do need to start early.
You need a laser. Why can't you just put a big mirror? I mean, you're not trying to reconvert the light to power on the...
I love this guy. I love this guy. This is so good. The reason that you need a laser is severalfold. The sunlight, if you just direct the sunlight is going to do almost nothing, because you can't concentrate it enough. The thing that's working for you here that makes this so effective is that laser light, you can focus it down to the point where it basically explodes the material off the asteroid. It's that material exploding off the asteroid because of the concentrated laser light that this works. Sunlight will not work.
You can't use the same non-imaging concentrators?
It won't work. You have to. We're really cranking things up here. The point is, once you get over that threshold of making it into coherent light, suddenly the intensity of the light, you can go, because you can concentrate in time and in space, we can go up by 18 orders of magnitude in the intensity of the light. This is the thing that most people who don't live in this world don't appreciate. They think, well, you got some concentrators, the focus will take a big magnifying glass, which gets some sun, and do the same thing. Won't happen. In a takes a while to learn this. You know, I spent 10 years struggling with this, and the thing you finally realize is, whoa, you know, this thing becomes, you know, 1,000 million times more effective once you do it this way. And it takes a while to kind of appreciate next few grads.
Well, so is it power measurable or not? Can you measure it?
Oh, sure, you can measure the power. Yeah, we work with maybe you have to measure things. One of the arguments is, how much does this cost? It's hard to say, but I would say over 10 to 40 year time, it depends, like everything else in space, on getting the cost of launch down, and the amount of power you can get goes up. And this is one of these few space projects that can make money. Basically, this is a alternative to oil. You don't have to go over and fight people in the Mideast for oil and power. This is another source of power that's rich, and it's available to everyone, and it's free. And that could be great. Okay, let's see. Can we do this, basically? And the answer is, if you look at the fundamental physics of doing this, the answer is it's certainly allowed by fundamental laws. You have to think about something about what you're doing, but it's allowed. That the strategy of getting there is one of the great virtues of this approach is you don't have to build a $600 billion system to try it out the first time. You can build a small-scale system, and then you can take that small-scale system and improve the concept and then scale it up another notch. Next. Conclusions. Okay, this is allowed. There are basically 4 areas of technology maturation that are required. You have to do this. It's not easy. You have to do something, but you know what to do. These are difficult to do, but they're not impossible. And the cost-benefit analysis, when you're getting an alternative source of power that's inexhaustible, cost-benefit analysis looks very favorable. Next. Anything else? These are students at the University of Alabama, Huntsville, who work on this project. My thanks to them. They were very stimulating and helpful in developing these ideas. Thank you.
Okay, time for a couple more questions.
Toward the end of, you showed the picture of where you were bringing a beam of this down to Earth to use it.
Yeah.
For some, what happens when these beams go into the atmosphere? Does that do anything to them?
The atmosphere will influence the beams. It's like it's just like images are aberrated if they come through the atmosphere. There's a lot of work that's been done by the Department of Defense on how to control laser beams so that they can propagate through the atmosphere and not be distorted in such a way as to prevent them from reaching their target. So there is a way to handle that. It's not a big deal. You prefer dry areas and that's the sort of place where it's not propagating.
I see. And how about the other way around then? What does the beam do to the atmosphere? Is it going to rouse the environmentalists?
Not a big deal. But, yeah.
I'm sorry, I missed the first part of the talk, so I'm not sure you covered this, but there's I believe it's in the documentation, it's a microwave-based solar power system,
Yeah.
sending power via microwave back to Earth. Do you use those systems?
Microwaves will not work. Okay, the reason is microwaves have a wavelength that's 10,000 times longer than the wavelength of visible light. And when you turn that into dollars, the amount of dollars for a microwave system and the size of the microwave system makes it cost prohibitive and basically impossible. So there's been a lot of talk about microwaves, but the one place where microwaves might be useful, if it came down to Earth, to the area close to Earth in low Earth orbit, and then you transform the power that you received optically over long distances to microwave power and beam it from close by the rest of the path down to Earth. That might be a place where microwaves would be useful.
Okay.
I do have a question, Professor. Well, you said that this type of power is measurable, then how do you increase or decrease it? Can you increase it or decrease it since it's measurable?
Are you talking about the power in our laser experiment or?
The sunlight power?
What would we, if we had this concept where we beam power, we change the amount of power?
Then how do you increase it?
You could vary it some. The way you excite the laser system is you take sunlight and you pump, you direct the sunlight into the laser. You could take the mirrors that direct the sunlight into the power of the laser, and you could turn one of the lasers in such a way that it wasn't being used. That would be, I think that we haven't emphasized the adjustability of the power. There are things you could do. I think it's like a power system. If you have a power station that produces a gigawatt of power, you try to use that power, you may send it to different places. I think it's more likely that what you do, because it's going to be beamed, you can send it to a lot of places. If you're sending it to a receiving site and you only wanted half the power, you could take the power that you would have sent there and just send it to another location.
How do you know when you have too much or too little power, or when you have enough power?
I think that depends on the consumer. It's like any power system. It's hard to come up with anything that's too much power.
Okay, we're just about at the end here.
Is there a storage problem on the other end once you've converted the power, let's say, for satellite use or something? Or do you have to track it in order to give it a continuous source of power?
If the receiving side is moving, of course, the beam is like the laser pointer beam. You have to track and follow that location. Of course, if it's distant, it doesn't move in angular distance very rapidly, but you do have to have an extremely precise pointing system that, again, the pointing system pushes the limits of what would appear to be feasible at this time. It's a demanding technology. As far as storage goes, the receiving site can do what it wants. It could use batteries, it could convert water back to oxygen, hydrogen, there could be various alternatives.
Okay, thanks.